Could a black hole the size of a glass marble be older than the sun and be passing through our planet right now? It sounds like science fiction, but it is a genuine possibility that astronomers take very seriously. Hold that thought and imagine holding out your hand. Picture a smooth, ordinary glass marble resting heavily on your palm. Now stretch your imagination and imagine that this single tiny sphere contains the entire mass of the Earth. Every ocean, every mountain, every continent crushed down into a space you can close your fist around. That is a black hole in miniature. Some black holes wandering our galaxy may be exactly that tiny, and they may be older than every star you can see in the night sky. Unlike the black holes we usually hear about, these would not be the collapsed ashes of dead suns. They would be ancient relics from the universe's very first moments, still drifting quietly through the dark today. To understand where they came from, we have to look back to the fraction of a second right after the Big Bang. The cosmos was not a vacuum yet. It was a dense, incredibly hot fog. It was a boiling ocean of energy and raw particles, packed tighter than the core of any star we know today. The pressure was unimaginable. In that chaotic inferno, the universe was not perfectly smooth. Rare patches of this fog were just dense enough and squeezed just hard enough by the expanding cosmos around them to collapse straight into black holes. We call them primordial black holes. They formed before the very first atoms cooled, long before the first light ever freely crossed the universe. Whether any of these ancient shadows survive to the present day depends on a slow, microscopic leak known as Hawking radiation. Stephen Hawking revealed a profound truth. Black holes are not entirely black. At their very edges, quantum physics forces them to glow just a little. Over vast stretches of time, they lose energy, they evaporate. Because of how this radiation works, the tiniest black holes evaporate the fastest. Anything much lighter than about 500 billion kilograms, roughly the mass of a large mountain, would have completely boiled away by now. But heavier ones could still be out there, surviving in the cold for 13.8 billion years. This is where mass and size stop making sense in everyday terms. A black hole's point of no return, the event horizon, scales perfectly with its mass. Give a black hole the mass of our sun and it is a few kilometers across. Give it the mass of the Earth and that absolute abyss shrinks to about 9 millimeters across. That is literally the size of a marble, a whole planet's worth of gravity fitting effortlessly in your fist. If you shrink the mass down to the weight of our moon, the edge of the black hole would be 1/10 of a millimeter, like a grain of fine sand. Go down to the mass of a mountain, and the black hole is roughly the size of a single proton. The greatest question in modern astronomy is what role these tiny shadows might play in the universe today. We know that a mysterious, invisible glue called dark matter holds galaxies together. Could this missing mass just be swarms of these ancient, tiny black holes? It is a deeply tempting thought, one that scientists have pursued for decades. The problem with that beautiful idea is that dark matter, even in our own stellar neighborhood, is incredibly spread out. In the space around our solar system, the dark matter is so thin that a room-sized volume holds less than a grain of sand in mass. If all of that invisible mass was locked up in tiny black holes, they would be profoundly rare. Our galaxy might be full of them in absolute numbers, yet they would be spaced staggeringly far apart. Even in a crowded Milky Way, the nearest tiny black hole could easily be further away than our own moon. Close passes by the Earth would be an incredibly rare lottery. Most of the time, they would simply drift like quiet, ancient fish in a huge, dim tank. If you are enjoying this kind of calm, cosmic exploration, you can subscribe to StarDraft for more. We make simple, deep dives into one wonder of the universe at a time, exploring the scale of it all. So how would we ever spot something so small and completely dark? Gravity gives us one very elegant trick. When a tiny black hole crosses exactly in front of a distant star, its intense gravity bends the star's light like a magnifying glass. To us, the star briefly and sharply brightens. It is a cosmic blink that can last from a few minutes to a few hours. For years, international teams of astronomers built massive sky surveys specifically to watch for those blinks. They aimed their telescopes at the dense star clouds of our neighboring dwarf galaxies, staring at millions of stars night after night. They did find a few mysterious brightening events, but nowhere near the numbers you would expect if all dark matter was made of these little black holes. On a remarkably clear winter night, astronomers using a giant telescope in Hawaii pushed even harder. They attached an incredibly powerful camera and stared at the entire nearby galaxy of Andromeda for an entire night. They watched millions of stars simultaneously. If tiny moon-sized black holes were common in the space between us, a handful of those stars should have noticeably flared. The shortage of those fast blinks delivered a sobering truth. It placed incredibly sharp limits on how many primordial black holes can exist at certain masses. Especially in the range of heavy asteroids up to small moons, the math simply does not allow them to be the main ingredient of dark matter. The sky is too quiet. There is another way to listen for the ghosts. The lightest black holes, the ones just barely heavy enough to survive from the Big Bang to today, should be ending their lives right now. Their final moments would not be quiet. They would vanish in a blinding, hot flash of gamma rays. Telescopes that watch the sky for high-energy bursts see no evidence of these local pops. What about the much larger primordial black holes? They would not vanish at all. Instead, as they drifted through the early universe, they would have slowly fed on raw gas, heating it up and lighting up the space around them. That extra energy would leave unmistakable scars in the cosmic microwave background, the afterglow of the Big Bang. But our best maps of that first light look perfectly clean. Ripples in space-time offer one more way to look. If our galaxy was filled with black holes lighter than our sun, we would occasionally hear them collide. Vast gravitational wave observatories on Earth have searched for the unique, high-pitched chirps these tiny mergers would create. The fact that we have not heard a chorus of them sets yet another hard limit on their numbers. Put all these incredible hunts together, and large swaths of possibility are firmly ruled out. But the door is not fully closed. Very specific, narrow windows of mass still remain hidden from our instruments. The debate currently circles around masses roughly the size of a large asteroid. As new data arrives, these windows keep shrinking, but they refuse to shut completely. The next generation of telescopes is taking aim right at those remaining shadows. We are building giant new eyes on the sky that will map the positions of billions of stars with terrifying precision, watching for the tiny gravitational tug of an invisible mass passing by. We are scanning the heavens faster and wider than ever before. If they are out there, we are closing in. Now for an eerie existential thought experiment. Imagine an asteroid-mass primordial black hole drifting with the galactic halo. It would be moving at roughly 200 kilometers per second relative to us. If one of these silent wanderers were to pass directly through the Earth, it would cross the entire planet in about 1 minute, from the ocean surface, down through the molten core, and out the other side. Despite what movies might suggest, it would not swallow the world. It would barely touch anything. Its gravitational pull is incredibly intense, but it only acts over a microscopic reach. The actual physical energy it would deposit into the rock and metal of our planet as it passed would be vanishingly small. It would be a ghost, likely leaving no trace our instruments could ever detect. So why do astronomers care so deeply about something so impossibly rare and hard to find? Because the early universe grew monsters far too fast. We look deep into space and see gigantic, supermassive black holes existing just a few 100 million years after the Big Bang. They are too big, too early. Primordial black holes might be the hidden seeds that allowed those early monsters to grow. Even if they turn out to make up only a tiny fraction of dark matter, finding just one primordial black hole would change everything. It would be like digging up an intact fossil from the very first heartbeat of creation. It would prove that Hawking radiation is real, allowing us to watch the absolute largest scales of gravity and the smallest scales of quantum physics interact in the wild. In the end, the picture is profoundly simple and beautifully strange. Primordial black holes might be smaller than a poppy seed, yet older than every tree, every planet, and every sun in the sky. They remind us that we are late arrivals in an unimaginably vast story, a story where the strangest and most enduring relics hide in the absolute smallest of places. Whether these ancient phantoms actually exist or not, The search for them acts as a compass. It points directly to how little we have truly seen and how many secrets the dark still keeps. If that tiny marble of infinite gravity ever does turn up, it will carry a piece of the very beginning. And long after the last stars in the universe fade to cold iron, it will still be here. If you find comfort in the sheer scale of the universe and love space explored in plain language, subscribe and look around the channel. There are deep dives on dying stars, the scale of the cosmos, and the edge of everything. Drop a like if this journey sparked a thought. Stay curious, and I will see you next time.